Hello students, today we are going to see about crystal physics, which is our first unit in engineering physics 1. As of crystal physics is considered, what we are going to see is how the matters are being classified, and because of that how we are going to classify the solids as crystalline and non-crystalline solids, and some of the basic concept in engineering physics 1 and as well as the crystallography and crystal physics. First we can go and see how a matter is being classified. So as for the matter is considered, it is being classified into three types: solids, liquids and liquid crystal, and gases. And here it shows how the atoms are being oriented in different types of solids. Because of this orientation of atoms, the properties of all these materials changes. Sometimes we say conductors or insulators or semiconductors. So how there is a change or a variation in the properties of the material, and normally we say that several properties in the generalized manner. It is electrical, mechanical, magnetic, optical, thermal properties which differs from matter to matter and material to material. So even within a solid there is a variation in these properties. How these properties are being varied? Because of the orientation of the atoms in a crystal structure. And now we are going to see about what is by crystal physics. So as we all know that the crystal physics is generally called as crystallography in a major field of physics. And here we say that this is a branch of physics that deals with the study of all possible types of crystals and their structures and how the structures are being classified. And these structures are being studied with the help of X-rays, neutron beam and electron beams, so which is more vividly used in describing the crystal structure and the atomic orientations in all the crystals. Now we are going to see about how the solid materials are classified. The solid materials are classified into crystalline solids and amorphous solid. The amorphous solid is also called as non-crystalline solids. Once again, this crystalline solids is being classified into single crystal and polycrystal. The single crystal has a wide application when compared to that of a polycrystalline material, and the single crystal is very tedious to grow, whereas the polycrystal is very simple to grow. And how we are classifying a crystal into single crystal and polycrystal is based on the grain boundaries. What are grains? Grains are nothing but atoms. The atomic orientation throughout a crystal is the same, means we say that it doesn't have any grain boundary. A grain boundary is said to be a defect in a crystal, whereas the polycrystalline material has a lot of grain boundaries. That means the orientation of atoms differs from one part of the crystal to other part of the crystal, and it is very easy to go a polycrystal even within a day or within an hour, whereas a single crystal takes a month and even a month together to grow a single crystal. Whereas when you go for an amorphous non-crystalline solid, there is an irregular arrangement of atoms. There is no periodicity in the orientation of an atoms, and hence we say that this amorphous solids does not have any sharp melting point, whereas this crystalline solids do have a sharp melting point which produces its application orientation. And as for the broad classification, as we have seen, the units of matter, always it is made up of atoms or molecules or ions. Need not to be always an atom, need not to be always a molecule. So it can be a combination of atoms, molecules or ions. And this is what is uniqueness of the crystalline solids. So as we have seen that it has a regular and periodic arrangement of atoms in a lattice. So I will just come again to explain you what a lattice is in other session. So this crystalline materials, we say that they have an anisotropic nature. That means they are called as an anisotropic substance, and they have a sharp melting point, as I said before. Because of its sharp melting point, we can use it for a wide application. So as we all know that we are using a chip, that is a semiconductor chip, which is a silicon or a germanium. So, or a combination of a semiconducting material like gallium arsenide, gallium phosphide. So everything is a crystalline structures. We grow that crystal and fabricate it so that we can use for some of the electronic equipments. And these material, the crystalline solid, to be more specific, they have a regular shape. What does that regular shape means? As we have seen, since they have a regular and periodic arrangement of atoms, we say that it has a regular shape. That means even if it is being broken into number of pieces, the pieces will have the uniqueness in its structure. And as we have already seen, the single crystal, that is, which is also called as a monocrystal or a polycrystal, is a classification of a crystalline material, and it's a one crystal system or a many crystal system. So depending upon our applications, we use these classification, and these are some of the examples. So these are some of the elements we have seen in our periodic table, and these elements are nothing but are metallic crystals and non-metallic crystals. So non-metallic crystals generally that is silicon and germanium, which is a semiconductor, which also comes under a non-crystalline crystals, non-metallic crystals, sorry. So when you go for a non-crystalline solids, so as we have seen, it is a irregular arrangement or a randomly arrangement of atoms, and it doesn't have any sharp melting point, as we have seen, and this is isotropic substance. They are isotropic in nature. And here when we say that it doesn't have a sharp melting point, in the sense it has a range of melting point. For example, we cannot precisely say, for example, rubber is non-crystalline solids, we cannot precisely say that at this particular temperature the rubber melts, or at this particular temperature this transition is occurring. So it comes under a wide range of melting point. So what we say that it doesn't have that wide range, and these are some of the examples of a crystalline and a non-crystalline solids. And you can see very well here a cone. Okay, so there is a regular arrangement and a periodic arrangement which looks like a crystalline structure. And these are some of the examples of a single crystals, so in which there is a regular arrangement of atoms, and it need not be always, there can be a combination of a single crystal and an amorphous crystals. So here it is an example of a pyrite crystal, so where we can see a crystalline structure as well as an amorphous structure in a same material, so which is very unique. And these are some of the examples of, as I said that, so there are grain boundaries, and here we can see that the grain boundaries are being present, the grain boundaries. So these grain boundaries are nothing but a splitting or a wall of separation between two types of atomic orientation. So here you can see that here the atoms are oriented in a different manner, and here it is just like a domain structure in ferromagnetic materials. So just as such we can see that in our polycrystalline material also. And here normally this is what is a dimension of a grain. So it is about 100 nanometer to about 100 microns. You know that 1 micron is nothing but 10 power minus 6 meter. And this is a quartz crystal, so which possess a crystalline nature, and here this is going to be a diamond crystal. So as we all know that this is a loosely packed structure in all the crystal structures, so which glitters, which is very hard, but it is being loosely packed. So that we are going to see in our next session, the cubic structures, so how it is going to differ in its binding and the coordination number. So now the basic concept in crystal physics, so which is a very major thing before we go on to an elaborate manner what a crystallography is, what a crystal physics is. So first we go for what is a space lattice. Before going on to what a space lattice is, first we must know what is a lattice. A lattice is an imaginary concept. Now we consider our class. So in a class, for example, there are 50 chairs that is being present. The 50 chairs are nothing but the lattice point. And the student who is going to sit onto the chair is nothing but an atom. So we, for example, when I ask you where an atom is present in atmosphere, in a gas consists of atoms or molecules, we know that. But if I ask you to pinpoint where the gas is, you may see, you may think that it's a humbug question. But actually, the gases can be positioned, the molecules can be positioned at some imaginary points. That imaginary concept in a three-dimensional space is what we call it as a space lattice. And what is so unique about the space lattice is that we can consider that whatever point you are considering in a space lattice, each other point would be identical. For example, when you consider this point D, so how many lattice points are present or surrounding the D? We can count. So it's 1, 2, 3, 4, 5, 6, 7, 8. So that means for a lattice point D, there are 8 lattice points which is being surrounding. The same case exhibit for even when you are considering this A prime. So here also you can see that there are 8 points which is being surrounding. That means in a space lattice, which is an infinite array of a lattice point which has an identical surrounding. That means what? Each and every point seems to be identical. And here in order to know about the lattice length, so as I told you that this is going to be a very imaginary concept, how we are going to measure, how we are going to study the crystal structures. So there are certain concepts which explains what a lattice concept is, how the atoms can be, the bond length can be calculated, how the bond angle can be calculated, so which would be used in a research field. And actually here we can note a term known as an lattice translational vectors. So actually this name seems to be somewhat vague, but it is very simple. Lattice translational vectors are nothing but a distance between two atoms. So how we are going to represent a distance between the two atoms, that is what we call it as a lattice translational vectors. So it is very easy to calculate. So now we can just go in for that demo of how we are going to consider this lattice translational vectors. For example, this is an origin. This point P is going to be an origin. So I want to measure what is the distance of this lattice point from this P. For example, I take this as an P prime. So from P to P prime, we are representing by a lattice parameter which is A. Likewise, along the y-axis from P to P dash, we can represent by B. Likewise, if it is going to be a three-dimensional parameter, we can represent by C. That means it is a vector parameter. So A prime, B prime and C prime are going to be the lattice translational vector. So which is very, very important in calculating the edge length of any of the crystal structure. And why we are insisting upon this lattice translational vectors, lattice parameter, is that by varying this, we will be able to get a different crystal structure. So what it is very unique. And once again, if we want to calculate the angle subtended between x-axis and y-axis, y-axis and z-axis, z-axis and x-axis. So that is what we call it as an translational angles, which is represented by alpha, beta and gamma. So those three angles are very important in explaining different types of crystal structure. So when we say that when the parameters are being made equal, A is equal to B. So as for here, I have just explained with the 2 dimension, but when we go for a crystal structure as such, it's going to be a 3 dimension. So wherein we will be considering 3 parameters, A vector, B vector and C vector. So now what a crystal structure. So now we have seen what is meant by space lattice. So lattice is going to be an imaginary point, and there is another term which is called as a basis. A basis is nothing but a single atom or an assembly of atoms, so which is being common in composition, orientation, so which group together with the lattice to form what is known as a crystal structure. For example, just benches alone in a classroom doesn't make a classroom. Benches along with the students make up the classroom. So just like that, so when you are considering this lattice point alone is not a crystal structure. It is just an identification. It is just a place where the atoms can be seated. So if you are making this atoms or an assembly of atoms, it need not be a single atoms. For example, if you are having NaCl, so or CaF2. So CaF2 means the basis is going to be 3. NaCl means the basis is going to be 2. So just like that. For example, if you are just having a sodium alone, so that the basis is going to be 1. So it is an atom or a group of atom or an assembly of atoms which group together with the lattice, which forms what is known as a crystal structure. So this is what happens. So now we can just see that. So how the basis goes and seats upon these points so that it produces what is known as a crystal structure. So this is how we get a crystal structure. For example, when you are having a diamond is made up of a carbon. So when all this lattice point is being occupied by carbon atom, that we call it as a carbon structure, which is normally a graphite structure or a diamond structure. Okay. Now another important concept which we call it as a unit cell. So this unit cell, as you all read in your lower classes, it is a fundamental building block. So normally the repetition of this unit cell is what we call it as a crystal structure. So here you can see that an orange, so which is being just cut into an equal portions. So when you are just going to combine this octant of a sphere, you get what is a sphere, that is your full orange. So just like that, so this is a normal cubic structure, and here you can see that the atoms which is being present and which is present at a different position of the lattice, which produces an entire crystal structure. So this is an HCP structure. And here it is a cubical structure. So when you are just repeating the cube, and we produces a larger cube, so which is going to be an original structure. So that means it is not necessarily, for example, if you are having 10,000 of atoms, I want to study about the crystal structure of 10,000 of atoms. It's a very tedious process. So in such a way, what we can do is that when a unit cell is taken aloof, and when its properties, when its characteristics is being studied, we will be able to study about the entire crystal structure. So what we call unit cell as a fundamental building block. So the repetition of which produces the entire crystal structure. So when we study about the unit cell, the entire crystal structure can be studied. So the crystallographic axis. So already in the space lattice, I just mentioned about the translational vectors and the translational angles, which is called as an interfacial angles. So this is what is, so for example, I consider a cubic structure. In a cubic structure, I just draw three axes, which we call it as an, normally in coordinate axis means we represent as x, y, z, and here these axes are called as crystallographic axis. So here you can see that this cube intercept at a different position, A on x axis, B on y axis, and C on z axis. So when we measure the distance from the origin O to A, that is one translation vector, OA is equal to A vector, OB is equal to B vector, and OC is equal to C vector. So this makes a translational vector. When we want to measure the angle, so how we are going to measure the angle? The angle is between OA and OB, OB and OC, OC and OA. So when you are measuring the angles between different crystallographic axes is what we call it as the translational angles, or generally we call it as an interfacial angles. So as I said, these interfacial angles and the translation vectors are the determining quantity of a particular crystal structure. So this translation vectors is also called as the primitives. We call it as by different names. We can know what are the different names by which we are calling a single term. So primitives, translational vectors, then lattice constants. So these are the different names by which we explain these length. And as I told you that we call it as an interfacial angles or an interaxial angles, which is alpha, beta, gamma. So if you're having more of crystal structures, even we can classify as alpha dash, beta dash, gamma dash, etc. Okay. So now when we studied about a unit cell, we have studied about what is an important parameters, which we call it as an crystallographic parameters. An important term is a primitive cell. So when we call a cell to be a primitive cell and when we call it to be a non-primitive cell. So primitive, that means when a unit cell contains only one atom. So now I think it's difficult to understand what a primitive cell is. So when I just go into a crystal structure, I think that would be easy for you. So now we just go for what a primitive cell is. A primitive cell is a one in which a unit cell contains only one atom. And as of the whole of the element modern classification is considered, the only element which is primitive in nature is polonium. So as of the element that has been discovered is only the polonium, which has only one atom in its single cell, unit cell, so which we call it as a primitive cell. So all other cells are non-primitive in nature, that is even if there is more than one atom, they are called as a non-primitive cell. So some of the example of the primitive cell is a simple cubic unit cell. As I told you that the only element which possesses the simple cubic unit cell is going to be the polonium. The other comes under BCC, FCC, HCP. So all other unit cell comes under this non-primitive cell.